Let's consider elastic collisions now. So in most of the everyday collisions that we see, some of the initial kinetic energy is lost to other forms of energy. So most everyday collisions are inelastic. A nice example of an elastic collision is macroscopically when molecules collide with walls. We assume that no kinetic energy is lost. So this is where our ideal gas laws essentially come from. So let's consider the equations that we can use to describe elastic collisions. So in elastic collisions, both momentum and kinetic energy are conserved. So we can describe the conservation of kinetic energy as m1u1 plus m2u2 is equal to m1v1 plus m2v2, and the conservation of kinetic energy as a half m1u1 squared plus a half m2u2 squared is equal to a half m1v1 squared plus a half m2v2 squared. Now in that equation there's a half in all of the terms, so we can just cancel them out and write the equation as m1u1 squared plus m2u2 squared is equal to m1v1 squared plus m2v2 squared. So let's have a look at a problem that we can solve using these equations now.
So our question, two spheres approach each other head-on with the same speed and collide elastically. After the collision, one of the spheres with a mass of 300 grams is at rest. Part A, what is the mass of the other sphere? Part B, what is the speed of the two-sphere centre of mass if the initial speed of each sphere is 2 meters per second? Okay, so whenever we're approaching a question, it's a good idea to start by drawing a diagram. So initially, we've got a sphere, let it have mass m1 here, and it's travelling with a speed u towards a second sphere, with mass m2, and m2 is equal to 300 grams, and this is travelling in the opposite direction, also with speed u. And then after the collision, the m2 sphere is at rest and the m1 sphere is going in some direction with some speed. We'll call the speed v1, but we don't know what it is. Okay, so let's write down the equations that we have to describe this situation. During collisions, momentum is conserved. So we can write, well, m1u plus m2, and u2 is minus u, because it's got the same magnitude but opposite direction, is equal to m1v1 plus m2v2, but v2, that's the speed of this sphere here, so we've got v2 is equal to 0, so this term here is 0. So we can rearrange this and we can write, well, this means that v1 is equal to m1u minus m2u over m1, which we can take u out as a common factor. So this is m1 minus m2u over m1. Okay, so now we've got an expression for the velocity of this sphere m1, whose mass we don't know after the collision. Now we are told in the question here that they collide elastically. So if they collide elastically, it means that a half m1u squared plus a half m2. Now that will be minus u squared, but the minus disappears when we square it, so it's still u squared. It's equal to a half m1 v1 squared, and we know that v2 is 0, so I'm not even going to bother writing that down. So these halves occur in every term, so they cancel each other out. So we can write this as m1 plus m2 u squared is equal to m1 v1 squared. Now just above we have come up with an expression for v1 here, which we can substitute in here. So we now have m1 plus m2 u squared is equal to m1 times, now it's v1 squared, so we've got m1 minus m2 squared u squared over m1 squared. So we've got an m1 on the top and the bottom here, so one of these will cancel out. So we have let's expand this square. So we've got m1 squared minus 2m1 m2 plus m2 squared u squared all over m1. Now I'm going to multiply both sides by m1 to get the m1 off the bottom here. So we've got m1 plus m2 u squared. So I'm just going to expand this bracket now. So I've got m1 squared plus m1 m2, and then both of these terms are times u squared. So we'll put the u squared in there, and that's equal to this term on the right hand side. So this just comes here. So this is equal to, and expanding the brackets, m1 squared u squared minus 2m1 m2 u squared plus m2 squared u squared. Okay, now looking at this expression here, some of these terms occur on both sides, so we can cancel them out. So m1 squared u squared, that occurs there and there, so that'll cancel out. So let's write this as, we shall now move this part over to this side. So we have, there's two of this term here and then there's one of them here, so they add together and we get 3 m1 m2 u squared is equal to m2 squared u squared. The u squareds cancel out, one of these m2s cancels out, and we end up with m2 is equal to 3m1. We have m2 is 300 grams and we're trying to find m1. So m1 is equal to m2 on 3, which is equal to 300 divided by 3, so that's 100 grams. So there was quite a lot of algebra, but we got there. We found out that the mass of the other sphere was 100 grams. Okay, now I'm going to scroll up a little bit to give us some extra space for part B. Now in part B, it says, what is the speed of the two spheres' centre of mass if the initial speed of each sphere is 2 meters per second? Okay, so what we're going to need to use here is that the speed of the centre of mass does not change as no external forces act. Okay, so we've got internal forces during the collision but no external forces. So the V for centre of mass final is the same as the speed of the centre of mass initially, and we can calculate the speed of the centre of mass initially. It'll be m1u1 plus m2u2 over the sum of the masses m1 plus m2. And we can substitute in all these things because we've just calculated that m1 is 100 grams. And because I've got grams on the bottom and grams on the top, I don't even have to convert to kilograms. So I've got 100 times. Now the initial speed we're told is 2 meters per second, but remember they're going in opposite directions. So this one will be plus 2 meters per second, and this one here will be minus 2 meters per second. So let's substitute that in here. So that's times 2, and then we'll have minus 300 times 2, and then that's over 100 plus 200. Oh, sorry, 100 plus 300. And so we've got 200 minus 600 over 400, and so this is equal to minus 1 meters per second, or 1 meters per second in the same direction as the 300 gram sphere.
So now that we've looked at elastic and inelastic collisions, we can give a really nice explanation of this Newton's cradle experiment. So I'm sure you've all seen this experiment before. With the Newton's cradle, if you release one ball from this end, you get one ball coming out this end. If you pick up 2 balls and release them, you get 2 balls coming out this end. And if you release 3 balls, you get 3 balls coming out. But now we can explain why this is. This is actually an elastic collision. So because it's an elastic collision, we've got conservation of momentum. So we know that whatever mass we're releasing, if this is m1, then it's got momentum m1 v1. And this is our second mass coming out of the collision. It's got mass m2 and it's moving with some velocity v2. But because it's elastic, kinetic energy is also conserved. So we've got a half m1 v1 squared is equal to a half m2 v2 squared. And we can cancel out the half to get m1 v1 squared is equal to m2 v2 squared. But now let's divide these equations by each other. So we're going to divide our kinetic energy equation m1 v1 squared equals m2 v2 squared by our momentum equation m1 v1 equals m2 v2. And this tells us that in order to have both of these hold, then we need to have v1 equals v2, which is why the ball comes out the other end, or the two balls come out the other end with the same speed. And then once we've worked out that the speed needs to be exactly the same in this case, we can see that this means that the same mass going in must be the mass coming out. Now, of course, we can mess with this a little bit, so we can force it to be an inelastic collision if we put some blue tack, say, between these last two balls and release one ball. But you can see it comes to rest much faster, so it is losing its energy much quicker in this case because it is no longer an elastic collision, it's now an inelastic collision. So this is a really nice demonstration that you can do with students to show them conservation of momentum and give them a nice simple case to use the equations for elastic collisions.